Now we're going to talk about the binomial distribution. In order to demonstrate this distribution, let's consider a spin system in an external magnetic field B, as you can see in this figure. So we have consider and this is an ideal spin system, so there is no interaction between the spins. An ideal spin system, this is in an external magnetic field B, and it's at equilibrium. Okay, so you can see one example here. We have a total of n spins. This is basically showing us the directions of the moments rather than the spins. Remember, if you refer to the video on ideal spin system, you will see that depending on the sign of the charge, the magnetic moment and the spin can be pointing in the same or opposite directions. So therefore, what these arrows show here is basically the directions of the moments. Now I call P the probability that a moment points up. That the magnetic moment points up, and I call Q the probability that the magnetic moment points down. So because for a given magnetic moment I have two possibilities, it's either pointing up or down. With these definitions, I'm going to have P plus Q must be equal to 1 because I cover all the possibilities, or Q, the probability of being down, is 1 minus the probability of being up. Now I find that if the external magnetic field is 0, what would happen? Up-down moments have no preference. And why is that? Because it's an ideal spin system. I ignore the interactions between the spins. So in this case, I would have P is equal to Q is equal to 1 over 2. However, if the external magnetic field is not 0, there will be an energy cost for pointing opposite to the external magnetic field. And as shown in the figure, it is pointing up in the up direction. And ideal spin system, no interactions between spins, no spin-spin interactions. So this would imply that in this scenario, P would be greater than Q. And I still have this relationship, P plus Q is equal to 1. This is true for all possible cases. And I will have two scenarios. External magnetic field is 0. This would give me P and Q is equal to 1 over 2. If the external magnetic field is not 0 and it's pointing up, then P would be greater than Q. All right. And so these spin orientations are statistically independent because there is no interaction between the spins. So let me call here, recall that this means statistically independent spins. So that is to say, if one moment is up, it has no influence on the next moment being up or down. Okay, so let's say that for n spins, for a total of n spins, or n moments, let's say, lowercase letter n moments point up and n prime moments point down. All right, then I would have the total number of moments n plus n prime is equal to n, or the number of moments that are pointing down is the total number of moments minus the number of moments pointing up. All right, so I have this relationship between the number of moments pointing up and the number of moments pointing down. Then the question I would like to ask is, what is the probability that in an ensemble so I have number of up spins could be 0, 1, 2, all the way up to all the moments pointing up, and moments point up. So that is Pn. Given capital N spins, what is the probability that lowercase letter n of those point up? So that's the question I'm asking. Well, first of all, I have noted that these are statistically independent. So let me underline this one. So there is no interaction between the spins. And why? Because it's an ideal spin system. So without thinking too much about this, I have learned that for statistically independent probabilities, the probability of joint occurrence of events is just the product of the probabilities. So let me phrase what I'm trying to do here. The probability of a configuration I'm looking for where n moments point up, n prime point down. So this probability. Well, for each moment, because this is like throwing n coins or n dice, I have a probability p of being up. So for the first one, second one, third one, etc. And there are n ups I want, so this is going to be n factors. And that implies that n prime of them should be down. The probability of being down is q, 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 n prime factors. So I have counted all the possible, I have gone through all the moments and basically applied the probability of being up or down. And since they are statistically independent, this should be p to the n, q to the n prime. So that's what it seems. Now, the problem here is that I didn't ask for the first moment to point up, second moment to point up, nth moment to point up, and n plus 1 to point down, etc. I asked for the probability of having any n moments pointing up. So that complicates things a little bit. So because there are many situations where n moments point up. So I have to consider how many distinct situations I have where n moments point up. Okay, so this actually the answer is given by combinations. So in mathematics we call this combination, and that's the symbol we use. It's by definition the number of distinct configurations of capital N moments where any lowercase letter n of these moments point up or n prime point down. It's the same thing. This is called combinations of capital N objects in mathematics taken lowercase n at a time. So that's how we word it in mathematics. So that's combinations. All right. So let's think about this a little bit. So if I have this many number of distinct configurations where I would have any n of these moments pointing up, then the probability I would have for capital N moments, lowercase n of them pointing up, this is going to be equal to combinations where I have n moments pointing up, p to the n, q to the n prime, or in other words, this would be equal to probability of n, given we have lowercase letter n of those taken at a time, p to the n, q to the n minus n, because I have n prime is equal to capital N minus n. Total number of moments is the down moments plus up moments. So this should be my answer. Well, I have to find out how to calculate these number of distinct configurations, the combinations. Okay, so this is the way I think about it. So when a moment points up, I'm going to call this U. When a moment points down, I'm going to call this D. All right? So I'm trying to figure out how to calculate this number of distinct configurations. So this number is the number of times in which a U, which is up, appears n times in a configuration, in a distinct configuration. Okay, so for the system of capital N spins, I'm going to put the first up. So I have a total of capital N spins. So I'm doing this step by step. For the first up that I'm going to put, this can be placed in capital N places. The second up can be placed in n minus 1 places. The third up can be placed in n minus 2 places, and all the way up to the nth up that I'm going to put. This has to be in n minus capital N plus 1 places. All right. So if I call Jn, J capital subscript capital N lowercase letter n, the number of possible distinct entries okay, this is going to be equal to, because there are n different ways of putting u1, n minus 1 different ways of putting u2, n minus 2 ways of putting u3, all the way up to n minus n plus 1 ways of putting un, and this is mathematically equal to n factorial divided by n minus n factorial. That's the number of possible distinct entries, Jn. What is factorial? Basically, n factorial means n minus 1, n minus 2, etc., all the way up to 2, right? So this number, n factorial divided by n minus n factorial, is n minus 1, n minus 2, all the way up to n minus, capital N minus lowercase n plus 1. So that's basically telling me the number of possible distinct entries of these moments. Okay, now there is a problem though. So when we put u1, u2, un, etc., we can also change the order of them. So because we don't have distinct up values, all we care about is that we have so many number of up values in this case. So for n subscripts, I have u1, u2, un. There are n factorial permutations. What does that mean? Different orderings. So that when you look at the combinations, the number of distinct configurations where you will have n moments pointing up, this is given by Cn, the number of distinct entries divided by the number of permutations. So it's going to be n factorial, n minus n factorial, n factorial. So that is what I'm looking for. Number of combinations of capital N objects taken lowercase letter n at a time. Then I will have, for the probability of having any n moments pointing up in an ensemble of capital N moments, is n factorial permutations, lowercase n factorial, n minus n factorial. That's the number of combinations, distinct configurations where I have n moments pointing up. Then for each such distinct configuration, I have statistically independent moments, so p to the n, q to the n minus n. So this probability distribution given for n moments is called the binomial distribution. And you may be wondering why it's called binomial distribution. It is due to the binomial theorem. So also in mathematics, if you have two variables p plus q to the power n, this is given by binomial theorem. N equals 0 to n factorial over n factorial, n minus n factorial, p to the n, q to the n minus n. For example, if you have x plus y squared, right? So this is x squared plus 2xy plus y squared, etc. So these polynomial expressions are all given by this binomial theorem. So we have this binomial theorem. Okay. And due to this theorem, we're calling this binomial distribution. Now, this actually theorem tells me something about this distribution. So let's see what happens if I count the probability of having no spins pointing up. One moment points up, 2 points up, all the way up to n moments pointing up. Any n, any 0, any 1, any 2, etc. So that's actually the summation from n equals 0 to capital N, Pn. And that is basically because the probability is given by the binomial distribution, that is sum n equals 0 to n combinations of n objects given lowercase n at a time, p to the n, q to the n minus n, and this, according to the binomial theorem, is also equal to p plus q to the n. But what we know what p plus q is, it's 1 to the n, so it is 1. Therefore, we have here what we know to be the normalization condition. So this is normalization condition when I consider all the possibilities. No moments point up, 1 moment points up, 2 points up, all of them point up, etc. Add them all together. So I will have the total number of possibilities exhausted, and the probability will be normalized to 1. Okay, so as an example, I would like to look at the n equals 4 ideal spin system. So this is n equals 4 ideal spin system. Let's look at this as an example. All right. So the first possibility I have here is all of them are pointing up. So n is equal to 4. So let me consider this case. N is equal to 4. N prime is equal to 0. As you can see here, I have only one configuration that gives me this. So combinations for 4 spins taken 4 at a time should be equal to n factorial, 4 factorial, n minus n factorial, n factorial. So this is going to be equal to 4 factorial, 0 factorial, 4 factorial, which is equal to 1. 0 factorial by definition is equal to 1. So indeed I find 1. For the second possible scenario here, I have 3 ups. So n is equal to 3, n prime is equal to 1. How many number of configurations do I have? Well, I just listed them all here. Up, 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 down, down, up, down, up, down, up. So these are the distinct configurations where I have any three moments point up. So what is the number of combinations of four objects taken three at a time? It is n factorial, n minus n factorial, n factorial. So this is going to be 4 factorial, 1 factorial, 3 factorial. That is 4 times 3 factorial, 1 times 3 factorial. These will cancel. I will find indeed a number 4. So let's try it one last time for this one. So here I have n equals 2. N prime is equal to 2, combinations of 4 objects taken 2 at a time, 4 factorial, 4 minus 2 factorial, 2 factorial. So it's 4 factorial, 2 factorial, 2 factorial, 4 times 3 times 2 factorial, 2 times 1 times 2 factorial. So I will find this is going to give me 2, 6. So indeed, I recovered the number of distinct configurations that I can see here. If on the other hand, for this one, I look for number of distinct entries, that would be J42. That is 4 factorial divided by 4 minus 2 factorial. Here I would have 4 times 3 times 2 factorial, 2 factorial, 12. You see, I would be overcounting the number of distinct configurations. So this is the number of distinct entries. So let me clarify what I have done here with the following example. So I'm considering the number of distinct entries for 4 spins taken 2 at a time. It is 4 factorial divided by 4 minus 2 factorial. So this is equal to 12. So that's exactly what I did just now. Now I want to figure out why am I overcounting this number of distinct entries. So look at what I have done here. So I have put the first up U1, second up U2, third one is down, fourth one is down. But I can also change the order of these two ups. I could have U2 for the first moment and U1 for the second moment. And these two are labeled with the same thing, A. Why are they labeled A? Because in these two configurations, I have the same scenario. The first two moments point up, okay? If I go to the second scenario, first one up and third one up, so I can put U1 and U2 for the first and third, and I could also put U2 and U1 for the first and third. So this is equivalent to saying this. So these two are the same. So I can put U1 on the first one, U2 on the last one, or U2 on the first one and U1 on the last one. So that would be this one and this one. They are the same. So if I keep going like this, I see that I'm counting them twice because I have 2 factorial permutations or different ways of ordering the same in this the ups. So I have to divide what I see here by 2 in order to get the number of distinct configurations for these. It would be this J42 divided by 2 factorial, number of permutations, it is 6. So the distinct entries here are distinct entries A, B, C, D, E, F. And then I have the permutations of this that give me exactly the same configuration for having 2 moments pointing up. Okay, we will continue with discussion of this binomial distribution further. We will look at the way it is behaving in more detail in the next video. So let me summarize what we did. We have considered an ideal spin system in an external magnetic field B at equilibrium. And we have P, the probability that a moment points up, and Q, the probability that a moment points down. And obviously a moment can point up or down, so the probabilities add up to 1. P plus Q is 1. If the external magnetic field is 0, then there is no preference for being up or down because there is no interaction between these spins. It's an ideal spin system, and P and Q should be identical. They are 1/2. If the external magnetic field, on the other hand, is non-zero and is pointing up, the probability of a moment pointing up should be greater than the probability of a moment pointing down. So P would be greater than Q. And I recall that since I have no spin-spin interactions, these spins are statistically independent. So if one is up, it has no influence on the second one being up or down. For capital N moments, I said lowercase n moments pointing up, lowercase n prime moments pointing down, so that the total number of moments, capital N, is n plus n prime. Then I ask myself, what is the probability that in an ensemble n equals 0, 1, 2 to capital N, so I can have no moments pointing up, capital N moments pointing up, etc. N moments would be pointing up. So I call this probability P subscript capital N as a function of N. So I ask myself, what is the probability of a configuration where n moments point up, n prime point down? Well, first thing that comes to my mind, since these are statistically independent, so recall that we had for 2 coins, if what is the probability that both of them are heads? It would be 1/2 times 1/2, 1/4. So here I have P times P n times, because I'm doing this for n coins if you wish, so it's n moments, and n prime moments have to be done, so Q times Q times Q all the way up to n prime factors. So I should have P to the n, Q to the n prime. But then I realized that I didn't ask for the first one to be up, second one up, nth one up, and n plus 1 pointing down, etc. I asked for any n moments pointing up. So in this case, I'm overcounting these situations. So I have to consider the number of distinct configurations of n moments, capital N moments, where any small letter n, lowercase letter n of these moments point out and prime point down. In mathematics, that is called combinations of capital N objects taken lowercase letter n at a time. So my answer will be the combinations multiplied by P to the n, Q to the n minus n. So I consider all the distinct configurations where I have this situation. Then I tried to understand how to calculate these combinations. For capital N spins, I can put the first up U1 in n places, the second up in n minus 1 places, the nth, lowercase nth up in capital N minus lowercase n plus 1 places. So the number of possible distinct entries for these letters, U1 all the way up to UN, is n times n minus 1 all the way up to n minus n plus 1 factors. In mathematics, this can be written as capital N factorial divided by capital N minus lowercase n parentheses factorial. But for these n subscripts, U1, U2, UN, there are n factorial permutations, different orderings. So in order to get the number of distinct configurations, I have to divide the number of distinct entries with the number of permutations, which gives me the number of combinations of capital N taken lowercase letter n at a time. So the probability is then n factorial divided by lowercase letter n factorial, n minus lowercase n factorial p to the n q to the capital N minus n, which is known as the binomial distribution. And why is it the binomial distribution? Because if you are adding two numbers to the power n, p plus q to the n, that is given by the binomial theorem as n factorial over lowercase n factorial capital N minus lowercase n factorial p to the n q to the n minus n. For example, x plus y squared is given by this theorem. So if I add up the probabilities of having no moments up, or one moment up, or two up, or all of them up, all the way up to all of them up, I exhaust all the possibilities, and I find that with the binomial theorem, this addition gives me 1. So it is the normalization condition. Then I checked that these number of configurations that I'm getting for the case of the 4 ideal spin system is indeed working. I have explicitly written all the distinct configurations where I have 4 moments up, 3 up, 2 up, 1 up, and no up. And indeed I find that I get the right number. And also in order to understand what I did to get this number of configurations, I have looked at my way of placing these ups and downs in my list of 4 moments. So when I put my first up u1, second up u2 in the first and second moment, I realized that I could have done it u2, u1, down, down, etc. So the entries I labeled A, entries I labeled B, C, D, E, F. So they are basically repeated twice because I have 2 permutations. So by counting the number of distinct entries of u1 and u2 and dividing it by the number of permutations, I got the number of combinations of 4 objects taken 2 at a time. So that allows me to calculate the probabilities properly.